All right, welcome back, everybody, to the Additive Snack Podcast. I'm your host, Fabian Alefeld, and today I am super excited to, for the third time, have Paul Gradl back on the show. If you don't know Paul, you should know Paul, because Paul is a principal engineer at NASA and really the leading driver and voice for additive manufacturing at NASA. And therefore, today we'll talk about various topics regarding additive manufacturing that oftentimes fall into the space area, but I think oftentimes very applicable to various other industries as well. So we'll talk about big parts, we'll talk about new materials, we'll even talk about topics such as the applications in rockets and satellites and many more things. So therefore, whether you're a veteran in space or in additive, or if you're new to the industry and a completely different field, I think you'll gain a lot of insights from Paul's experience and from the topics we will discuss today. And therefore, without any further ado, Paul, welcome back to Additive Snack.
Thank you so much for having me, and appreciate the introduction on that. You know, it's a fun role that we have in the government side, being able to present and provide a lot of the information publicly. So I look forward to digging in.
Yeah, and in your government function, for sure, this is all research and insights that I think are all for the common good for everybody, especially in times where, we talk about bringing manufacturing back to the US. I think additive needs to be part of that conversation. And therefore, I'm really pumped to talk to you today. One of the things that more and more, I think, come up in the additive manufacturing space is materials. In the early stages of our technology, I think we've always tried to just work with a very limited number of materials that we knew really well. But I think recently we've really had an expansion, and not explosion, but expansion of new materials. And I think NASA has also been one of those key drivers of these material developments. Could you tell us a bit about what new materials you see coming to market, being in research, and how that is impacting the space of additive?
Yes, I think you're absolutely right. When we first started additive back in the early 2000s, a very limited number of materials, right? I like to compare it to the Henry Ford famous quote is, you can have it in any color you want as long as it's black. And I felt like that was additive. You could build it in any material you wanted as long as it was Ti 6.4 or stainless, 300 series. But I think in the last 20 years, since NASA has really dug into additive, we've expanded the database of materials that are available, not just available for development, but even available for flight applications. So we see materials across all the families now. All the aluminum alloys have really expanded, and you have a large pick from all the different series, 1000, 2000, 5000, 6000, 7000 series aluminum. Titanium, we're seeing a lot more titanium based materials. Of course, all the nickel based materials, which seem like they were made for additive, very friendly to build, all the different Inconels and Haynes alloys and nickel, cobalt, chrome. And then we're seeing even unique materials now. Refractory alloys are definitely one of the areas that are expanding. NASA's been developing some very high temperature and unique alloys in the copper family and oxide dispersion strengthened materials. And even we're seeing some additive in some of the platinum-based families as well. So I think it's exciting, right? Because we don't have our two materials anymore. And now we can really design for additive with the materials that we need, not just what's available to us. But I think there's also some education on that too, that people tend to pick what's in front of them, and that is a challenge we're having to get past. But it's no longer your grandfather's additive, right? There's new materials available and modern materials as well that provide a lot higher performance than we were seeing 20, 25 years ago.
Yeah, I guess we are 35 plus years into this industry where you can actually say it, not your grandfather's additive anymore. That's a unique saying that first shouldn't apply, but it actually does. Let me ask you this though. Okay, so we have a completely new set of material families. How does that development process, at least from the NASA side, typically look like? How do you start the investigation for a new material? Is that application focused? Is that material property focused? What does that process look like?
Yeah, I think anything that we're doing really has to start with a set of requirements. What are we trying to solve with this? We don't just sit around and say, hey, we want to come up with this new material and not have an application for it, because you have to design for that set of requirements. I have to design for the environment and understanding, what are the limitations of it. And that is why we have so many materials. I think a lot of folks that aren't necessarily in the materials world, again, they want to pick from like a handful of materials and apply it to everything. I think for us, right, having extreme environments, really high temperature, a lot of our applications, we need materials that are going to push 1100 C or 2000 degrees Fahrenheit. We have high pressures that, are approaching 5000 PSI, which I think is about 30 to 40 bar. Extreme pressures, extreme temperatures, high duty cycles, so fatigue, creep resistance. And then we even have unique challenges with different compatibility and some of the propellants that we use and some of the environments. You have to be compatible with hydrogen, for instance. So all these new alloys have a specific application in mind, and usually a certain set of properties that we're trying to meet as well.
Interesting. Can you highlight a few materials that you think are especially interesting to folks out there? And what I'm especially curious about is, obviously NASA develops these alloys with space applications in mind, but I think as you often see, these materials start to find applications in other industries that are not space related, right? I could see a super high temperature alloy finding its way into research of nuclear fusion reactors, right? Where we have not 2000 C, but a million C in a reactor, and we need to pull that energy out. Or I could find these harsh environments you're talking about. I could see applications in the oil and gas sector. So which type of materials do you think are especially interesting right now? And do they also apply to some non-space applications?
Yeah, I think this is one of the areas that I'm really excited about. And one of the things that I take a lot of pride in from the NASA side as well is we do something for our missions, and you get to see this expand across the supply base. One of the materials that we've been really focused on the last decade or better has been GR COP materials. Those are copper, chrome, niobium. They're a high temperature, high conductivity copper alloy that we use for combustion chambers in liquid rocket engines. And we've developed the supply base for that. We flew that with one of our commercial space partners a couple of years ago. We're seeing that used on a lot more space missions, but we're also seeing use of that now in semiconductor industry, where they're using it for heat sinks and cooling, active cooling, some of these supercomputers. We're seeing it in heat exchanger applications, even like mold making, where you need high conductivity, but you want high duty cycle, high strength, and some of these. Another alloy that we've been focused on the last few years is called GRX 810. This is developed out of Glenn Research Center, as GR COP was as well. And we partner across NASA and industry to infuse these alloys, again, not just for NASA missions, but making sure that we can have a supply chain set up. And we really want others to, find their unique applications as well in this. So GRX 810, it's a nickel cobalt chrome material. We use a nano dispersoid of yttria in there, which gives it creep resistance, high temperature capability, really, really good oxidation resistance as well. And of course, we're using it for rocket engines, but we're seeing use for it now in turbines. Obviously for rockets right now, but eventually it's going to be in land-based turbines. We're seeing DoD applications of this. And it's a material that's unique, being nickel-based, but it sort of straddles the traditional nickel-based materials with refractory alloys. is we're operating this material above 1200 C. And keep in mind that it melts a little bit higher than that, but we still retain sufficient strength at those really elevated temperatures. And I think one other unique property that we found with this, and the team up at Glenn has been doing a lot of testing for creep. And we find that we get over 1,000 times better creep resistance than standard alloys. So some of the nickel super-based alloys will fail after 50 to 60 hours at about 1100 C or 2000 Fahrenheit. And our GRX 810 has gone over 6,000 hours. And actually, we have some samples that are continuing to run beyond that as well. So additive has opened up sort of these new families of materials and new ability to make materials that we couldn't make before. And, we're taking some of that core technology from the GRX and the coating process, which is fully commercialized now. So you can go buy GRX 810 from a bunch of powder suppliers. But now we're expanding it to different alloys. We have some burn resistant alloys. So when you get in like a high pressure oxygen environment, any of your materials can be your fuel as well. So we have to design materials that are not going to burn in those certain environments. And we're using that same technology with the coating process to help us retain strength. And again, really exciting to see where this is going. And I think one other thing that's really neat about this is when we did alloy development 20, 30 years ago, it took years to do this. Now with like the GRX 810, we developed the material up at Glenn Research Center. They developed the coating process, and it was still a couple years to really develop the robust material. Some of our most recent materials, we've gone from the chemistry development and modeling all the way through powder and even making samples and parts within months. So we've accelerated the alloy development, as well. But of course, there's caution with that. One thing that I see out in industry, the challenge is that, you develop a new material and you want to go release it to the world, right? And I know for companies, of course, it's the sooner you can sell the material, and create revenue from that. But you have to go through proper characterization, parameter development, mechanical testing. So we want sufficient data to show that the material is going to fully meet all the requirements.
That's very insightful. I've been wondering for the past probably 12 months or so, ever since I saw the Google winning a Nobel Prize for their AlphaFold tool, which predicts protein structures and how they fold, which can rapidly accelerate the development of pharmaceuticals. I'd be really, really surprised if a similar application of AI would not also be applicable to material development, right? It's also a very complex process that typically today still requires a lot of experience, and that could be accelerated by technologies such as artificial intelligence. Is that even already somewhat a part of your development process when you talk about GRX 810 being developed in a matter of months versus years? And if not, do you see that on the horizon as well?
Yeah, so our initial material development, like the GRX 810, we use a lot of simulations and modeling techniques, both off-the-shelf software and some custom software that allows us to, model it thermodynamically, understand potential material properties with it, some of the limitations of it. So certainly that side of it has accelerated. We're not using AI or machine learning as much for the alloy development, but we are starting to use it more for some of the property characterization. Right now, and I think traditionally, to get a good set of properties, you go and you test hundreds and oftentimes thousands and thousands of samples with different lots of material. Now, we're still testing a lot of samples to get statistically significant data, but I can use some machine learning to help analyze some of that data and predict, further, okay, if I were to change this chemistry slightly or these parameters slightly, how is that going to change some of the properties? I don't see, as of today, that we're going to use that for qualification by any means, but I do think that'll help us accelerate understanding of some of the materials and, potentially help accelerate some of the qualification process. But with any of these AI models and machine learning is you have to have a really large data set to train your models. And I think that's something that we're still limited on. One of the challenges that I see with all this materials development, not just the new materials, but even a lot of the traditional, like I said, I think we can sort of say that now, right? Traditional materials are 20, 30 years old, is we have large data sets, but nowhere near compared to what we had with wrought alloys. So we still have a lot of learning to do on, getting thousands or hundreds of thousands of tests and samples and having these really large data sets that we can apply machine learning and AI to. And also being able to share this stuff publicly. I'll put in a plug for that, is I think we're seeing this property development sort of take place in silos, different companies, and holding some of that data tight, where we observe that challenge, and we've been trying to take on a role to do some property characterization, but eventually we'll be providing a lot of this data publicly for both the new alloys we're developing and some more of the traditional common alloys that we see in additive.
Yeah, interesting. No, that is true. I mean, today companies do see it as a competitive advantage in certain cases to have that data. It's also a big invest. So there's certainly some market dynamics that make it more difficult to have that huge publicly available data set that we could train agents with. But it's good to hear that is somewhat on your mind, and that there are some programs going on to collect that data from an NASA perspective.
Yeah, and I think some of it, maybe started a little bit selfishly in a sense, is when we were going to design with certain materials, and you go to your designer and say, I'm going to use this certain nickel-based material, and the first question they have is, well, what properties do you have for it? And I don't have anything. We make something up, apply some correction factor on it or some knockdown. So we have to do this, right? To make additive real, we have to have these properties. And again, from NASA's role, being able to put this stuff out publicly not only helps us, for our missions, but I think helps the industry as well, because we want to see others continue to add to those data sets.
Yeah, it's a good initiative. Switching gears a little bit, one huge part of additive that I think will continuously unlock new applications are materials, which we just discussed. Now, a trend that's been going on for a few years now has been size, right? Big machines, big parts. What role has NASA played in the scaling of additive and all that stuff?
Yeah, I think this is also a really interesting area that additive has grown figuratively and literally, right? Yeah. If you look 5 to 8 years ago, we were still talking about parts that were shoebox size. And now we're talking parts that are filling rooms. And we recognized that several years ago. As a matter of fact, in my role, when we first started additive, I worked with laser powder bed fusion, electron beam powder bed fusion for a while. But again, we were limited in the parts. I've always been I think my core technology development has always been in channel wall nozzles for liquid rocket engines. And these are often the largest part on the engine. So we're talking a couple meters in diameter and several meters in height. So, 5 to 8 feet in diameter and sometimes 10 feet tall on these. And I knew that powder bed fusion was not going to get us there, right? I didn't want to produce a whole bunch of powder bed fusion panels with the channels in there and try to weld a bunch of these together, because that was not going to solve the problem. So we started a bunch of industry surveys to figure out what capabilities were out there. And of course, that moved us more towards the directed energy deposition process. But traditionally, a lot of directed energy deposition was focused on forging, casting replacements, repair, and more coarse structure in the parts. So we've really had to push the technology as we want to do really thin walls with all these complex internal features and make it really large. And anybody that's worked with large parts and, thin structures, that it's a tremendous challenge. So, I think engaging and collaborating very closely with the supply chain, we've been able to solve a lot of those issues. And we've seen the machines grow in size, definitely. I think now we don't really blink our eye at seeing something that's a couple meters in diameter. I've seen some out there that I think are even pushing like 4 to 5 meters in diameter and 4 to 5 meters in height. So we're talking really large structures now, and I know that we're starting to see more and more like casting and forging type replacements with the DED processes, even some of the solid state processes like cold spray and additive friction stir deposition, really offer that large scale. But again, you have materials challenges with it, right? There's unique materials we use with these processes. If I'm using like a DED process, I'm putting more heat input into it, so residual stresses. So I think in the additive world, no different than the rest of manufacturing, there's nothing for free. We have to understand all those process sensitivities and limitations of the process. But I think industry has also been doing a good job collaborating on this and figuring out, what are the gaps and where do we need to research, where do we need to push the technology, and NASA has been behind a lot of that development.
Very interesting. 4 to 5 feet. What types of applications are we talking there? Are we talking tanks? Are we still talking engines? What are the use cases for these super large?
Liquid rocket engines is certainly one. The nozzle structures. We're looking at even like the combustion chambers as these get larger and larger, creating the jackets on these. So doing bimetallic additive manufacturing, tank structures. Some of the unique tanks that we need for like cryogenic fluid management, being able to store propellants in space or having orbiting gas stations essentially you need some unique tank structures with regenerative cooling in there and active cooling devices. But of course they have to be really large with these fine features. Support structures, really large structural type systems. And then we're even looking at, things like valve housings and large components that may have been a casting or a forging, but we may have challenges, right? That there is unique shops in the US that had a very special skill, and some of that knowledge has gone away, that generation has retired, and we're not able to either recreate or get the same quality out of it. So we're looking at additive for how do we solve some of those tough challenges.
I mean, it sounds like a lot. That's more than just engines or thrust chambers, which we may be talking about today. From what on an average commercial vehicle, I mean, I'm sure there's some others that leverage additive more than some of the other competitors. But what percentage of a rocket today is built additively, and do you see that shifting dramatically over the course of the next 5 years?
Yeah, it's really a small percentage. I think more recently we've seen additive used in propulsion in rockets, right? We have really complex components, extreme environments. We have unique alloys that are tough to machine and weld and braze and assemble. So additive is primed for that. So definitely rocket engines. We do see some applications on the vehicle side. Certainly worked with some of the commercial space partners where they were making tanks and other structures using additive manufacturing. But I think this is sort of really an important conversation and point that you bring up is we don't want to apply additive to everything. And often when I'm teaching classes, I'm always going to say, don't use additive unless you have to. Like if you break down the cost of additive, it is far more expensive on like an hourly basis than traditional machining and forging and casting. The material is more expensive, in terms of the feedstock compared to traditional manufacturing. So we really have to understand the use cases of it and when not to apply it. So I don't see additive taking over the manufacturing space. I see it as a supplementary technology. Can we use it to enhance performance and get unique geometry that we couldn't get before? Can we use it for these new materials? Can we use it as a casting or forging replacement where we have supply chain challenges on it? But I don't see it again as like competitor, to traditional manufacturing, but something that we should be supplementing. So, your question in terms of like launch vehicles, no, I don't think it's going to be, probably not even 30% or 50% of a launch vehicle. I think it's going to be a very small percent, but it's going to allow us to improve performance and do things that we couldn't do with traditional manufacturing. And then, overall, we're optimizing the vehicle using all these techniques.
Yeah, it's a tool in the tool belt. That tool is getting sharper and better as we go, and so do the other tools, right? So collectively, I'm sure that will have a continuous impact. You also mentioned, besides the launch vehicles, the payload and other applications such as satellites, moon landers, gonna go to Mars. What about in those types of applications? Does additive play a bigger role there due to also rate reductions or complexity, or less of a role? How do you view that field?
Yeah, I think we're seeing more application additive probably in some of the in-space operations, satellite, landers, right? Even some of our like nuclear propulsion, that's probably more of a materials challenge there. But like in satellites, for instance, we're starting to see unique designs in brackets in propulsion systems, brackets where I can truly optimize using like generative design or topology optimization and start to reduce weight overall on these and make unique structures, again, that can house my propulsion and payloads and start to consolidate a lot of components. So I think it simplifies some of that. We're starting to see more and more use of additive for some of the propulsion systems on satellites as well. So like in-space thrusters is using refractory alloys and some of these unique materials that allow for longer life in higher temperatures and being able to combine your small propellant tanks with the thrusters themselves. So there's a lot of applications, across satellites and in space using additive.
So the challenge there is, I'm guessing, also the temperature changes that occur in space over, what's the lifetime of a satellite? 20 years, 30 years?
Yeah, I think it depends again on the satellite, but as long as possible, right? The real expense is in the launch of the satellite for some of these larger satellites, and of course, satellite itself is fairly a large cost. So you want to be able to, have that survive for decades. So again, really, really challenging environment on that. Like you mentioned, I have these big temperature swings from like extreme cryogenic temperatures all the way up to elevated temperatures, depending if I'm in the sun or in the shadow of Earth, and also the vacuum, environment. And then I have to stay up there for decades, and depending on the configuration of some of these, there might be other fatigue challenges on this. So there's extreme environment and being able to optimize for weight really provides challenges for any manufacturing processes.
Yeah. I think the one thing that some of the non-additive media likes to talk about is also in-space printing, because that seems like the perfect science fiction tool. I think us in the industry are a bit more skeptical about it. What's the truth there? Like if we build a base on the moon or on Mars, is additive really one of those technologies that can help us to build a habitat out of local materials, or is that just science fiction?
No, we are actively working that. And when we return to the moon and eventually go on to explore Mars, we're going to have to create components and roads and habitats and power plants, and you're going to have to use the local resources to do this. So we have a powder bed machine actually set up right now where we're looking at lunar regolith simulants. So essentially you're printing glass from that, it's a starting point, but I think the objective there is, can we down the road process some of the regolith, and what elements can you extract to create other materials, or can you use the regolith to combine with some other binder and then be able to create like a concrete type material, or to be able to create structures and roads. And so absolutely, I think additive is going to play a role there. It just may not be the additive that we're thinking of. These small machines are going to be large gantry systems. And I think it's neat that we're even seeing some of this in the construction industry right now. You're seeing some unique architecture designs because of additive. I know that we have a parking garage here in Huntsville that has some really unique ornamental features on it that were all 3D printed in concrete. And you see habitats, and I think there was even a restaurant, one of the popular chains, that had used, concrete additive.
I saw that.
So, it's taking those same contexts terrestrially and applying them to the moon and Mars. Absolutely. I think that is something that we're going to have to advance further.
Interesting. Yeah, even in Austin at the one of the convention centers where we used to have a conference, an additive conference here. There is a little structure in the back that's also 3D printed by a local company. Is there enough gravity on the moon for powder bed? I mean, that's a question that I ask myself. Or would the particles, I guess you have to reimagine everything, but is that even realistic?
Potentially. I think you might have enough gravity on the moon to make powder bed feasible. I'm not sure about quality of your feedstock and contamination control, because it is a really harsh environment. I mean, a lot of the studies that we're doing, for lunar landers is just all the dust mitigation up there, trying to land a vehicle and you have a rocket engine plume that's just blowing dust everywhere, and that dust is going to cover your vehicle, and you have to think about all your bearings and wear surfaces. Well, that's sort of the same thing, when I'm trying to create a lab or environment to make parts. But yeah, I think it's feasible. I know a lot of the technologies we've been looking at for microgravity, though, like on space station, is really focused on wire-based techniques. But, with a little bit of gravity, that can help solve some of the challenges there.
Yeah. And so the regolith you talk about, it's moon dust, right? What type of elements can you find in moon dust? So when you say glass, I'm guessing silica, right? Is a key component.
Yeah, silica. Certainly there's been a lot of studies on being able to find, water in there so that we could extract oxygen, hydrogen, potentially methane out of some of the regolith as well. So can I make fuel? Can I make, propellants that I can use to either fuel my rocket engines and launch vehicles, or, being able to use that for power conversion. So I think, again, as we are sending up these commercial space lander systems, we want to continue to study and understand the regolith more, and really down select like what materials are going to be possible for us to build.
Interesting. I remember 10, 15 years ago, there was also some buzz about asteroid mining and printing off of asteroid materials. Is that still a thing, a consideration? Because there's some really interesting materials on asteroids, right?
Yeah, I don't know. Completely different area outside of my expertise, but there are some very scarce elements out there that if you can find a way to harness, some of those, then, elements that are very, very rare on Earth are just abundant in some of these asteroids. and would allow us to use some of these materials in modern electronics and, really bring down the cost of even like some of these refractory type alloys and, platinum based materials and things that go for thousands of dollars a kilogram. You could bring that down to, I don't know, a few dollars, I think, just because of how much is out there. That has always been, one of the talks as well, asteroid capture, and how do you mine these asteroids and how do you bring those back, right? So I think a lot of the trade studies just say that it's too cost prohibitive, but certainly I hope that those studies continue and somebody finds the business opportunity to do that, which would expand space even further. I think that's one of the things that we see as well, right? It's always been, a lot of space has been government funded for commercial launches and satellites, but in the last couple of decades, we see a lot more investments from private companies and wealthy individuals, finding opportunities in space. So maybe we will find those opportunities in the business case for asteroid mining. And maybe additive will play a part in that.
Yeah, I remember that company back then. They were even, I think, printing some of that asteroid material. I think they were even a Richard Branson backed company or something like that. It's been a long time, but okay. I have a few more topics for you. One is, sometimes when we talk, everything is rosy and awesome and beautiful and you have new materials, but things do go wrong, especially in research. One of the videos that has been shown now a few times also on different platforms and social media is, I think, an engine that's had a failure at a test stand. And maybe I can even pull it up real quick and you could kind of like talk us through what happens.
Yeah, so this was part of our long life additive manufacturing assembly. This was a project that I was managing, and one of our goals was to be able to show 50 starts on a combustion chamber. So putting it through the full duty cycles, showing reusability on this. And we actually tested a chamber 51 times, and we had a second sister chamber that was actually built in the same build. It was on a 400 by 400 build platform. We built 4 of these chambers. We said, let's go test this second chamber, right? We had success the first one. We tested this second chamber 8 times. And then on this 9th start, we had this issue that you just showed in the video. So first you see this developmental composite nozzle extension that comes off. We knew that was going to fail. It had a pre-existing crack in it.
So this you knew was going to happen.
That we knew was more or less going to happen on this test. We were expecting that. And sometimes when nozzles fail, you continue to run, right? Because I can still get information about the injector in the chamber. Mm-hmm. The chamber that you see there that just separated was not expected. Okay. And this is a very unique event that it was right at a build interruption. Okay. And prior to this, we had tested dozens of parts that we've seen build interruptions before. And it's one of those things, not that I'm saying it's normalization of deviance, but right, you see this happen before and you think, okay, well, maybe we'll be okay this time until it's not. And I think this is a really valuable lesson learned overall, because with anything that happens, any sort of failure, right, there's multiple pieces that stack up. In this, so we had the build interruption, which by itself, we have restart procedures, we've tested build interruptions, we have a lot of mechanical properties. We know that you can be successful with a restart. This particular one, with the entire build, we were seeing the porosity increase with the height of the build. And I think the particular powder that we had, there's more fines in there, and they're starting to accumulate on the cover lens. So you had less energy going into the part, and then when you had a build interruption, your heat gets cut off for a little bit, even though we go back and reheat that particular layer where we're not laying down powder. So I didn't say this was laser powder bed fusion. So we preheat that layer and then we continue on the build, and we saw that there was more porosity that congregated along that build interruption, that witness line, and you just lost load bearing capability. That's exactly where it separated. So it was one of those things that we want to prove this out on the ground, right? And understand all the process sensitivities. And there's a whole lot more details than what I described there in 2 minutes. But we just put a journal article out about this recently, that talks through the failure, talks through understanding what happened to the materials, how we tested, taking tensile samples and fatigue samples direct from the chambers and the sister chambers that we didn't test, along with trying to recreate that failure. So I think it's good to show successes, like you said, in additive, right? We like to show how great it is, but we also need some reality checks too on this. And I think we're past the hype overall of additive, and it's companies are looking at, like, how do we make this real? And this is a perfect case of making it real. Like, you have a failure, you need to understand what are the process sensitivities, how do we mitigate that in the future? And that, again, is really one of the great roles for government, is being able to provide all of that publicly and say, here are the lessons learned. We want to educate folks on that so that industry doesn't have failures.
Yeah, we need to fail in order to continue to grow and improve. Right? And there's an awesome data point that you guys generated here for everyone. I love that video. I wanted to show it.
I'm glad it's fully public. This was years back that we did this test, and we had a formal report, and I've presented it publicly several times, but it was time for us to put a bow on it and provide a fully public paper on that one. And I know that we will continue talking this one for a long time, because it's something that, as a design engineer, and really anybody working additives, you have to have a good understanding of the material now. And I think that those roles have sort of merged, that we're not as compartmentalized maybe as we were with a more traditional process. You have to understand all the nuances that additive has, and directionality and different processes and material properties that go with it when you're designing for it, or you could end up in a situation that you have a failure because you don't have anisotropy and you don't have material properties that you thought you were in a certain direction. So that's one thing that we push a lot when we're doing classes and education on this, is probably 25% of it or more just here's the materials aspect of it. Because with traditional manufacturing, we would get certificate of conformance from the casting house or the mill that made the material saying it meets these properties, and you don't get that piece of paper with additive because you're creating that material yourself. So I think it's really important to educate on that aspect.
Yeah, education is obviously a very important mission of NASA, but also I think very near and dear to your heart. We're also doing something really cool together. We just signed a Space Act agreements in order to bring Paul to even more people out there. You and Omar. Tell us a little bit about that masterclass that we're working on, and what participants can expect to learn.
Yeah, I am incredibly excited about this, and I wish we'd have done this sooner, because this is something that I have always wanted to see created. So what we're going to do in this class is we will be teaching morning sessions, and we're going to dive into all the nitty-gritty of metal additive manufacturing. What are all the processes? How do I trade for those processes and select those processes? What are the material aspects that I need to consider? Process parameters, post-processing, because you can't be successful in additive without post-processing. How do I qualify additive parts? How do I go through DFAM, design for additive manufacturing? So we'll be teaching sessions in the morning, but then we're going to take what we've learned in the class and we're going to go apply it, right? We're going to go build parts. We're going to go set up these builds and teach folks like what are the nuances of adding witness specimens and orientation and layout. How do I post-process these parts after I hit build on it, right? There's a lot of work to be done on that. So I think this is going to be incredible in terms of hands-on, engaging in discussion on all the nuts and bolts of additive, and something that honestly, like I wish, a class that I would have been able to take 5 or 10 years ago. And I think it's going to be really, really beneficial, and look forward to collaborating with all the industry partners on this one.
Yeah, I'm super excited for it as well. I will learn a ton myself from you, of course, but really to be able to bring that knowledge and experience out to folks. Yeah, it'll happen down in Austin. People will get access to labs, to the machines, everything that you mentioned, post processing. Really have a hands-on experience, but also soak up all that knowledge that you and Omar have accumulated. We'll add the sign up link to the show notes here as well for folks to sign up. Really excited about this one. What I'm also not necessarily excited, but impressed by, and where I think you are a great role model, is as a parent, you're a parent. The way that you engage your kids in additive manufacturing or in engineering, I would say in general. Just before we click record, you showed me some cool parts that you and your daughter came up with. I know you and your son also have a bunch of projects going on. Tell me a bit about how you incorporate that mindset at home, and how your kids have adopted that curiosity, which I think is so cool.
Yeah, I think it's important for us to be mentors, right, wherever we are, whether it be work or at home. And we're a big 3D printing family, right? Both at work for me and at home. So our FDM printer is running, probably near 24 hours a day. And it's really cool to see my kids adopt the technology, right? I think one thing as a parent, I want them to learn on their own. I don't want to necessarily force them. So finding their own interest in it. And my son, he's really engaged in like fidget toys that he can print, and then even making his own creations, being able to design on CAD and then having this come to life has really been fascinating for him, and I think for his teachers too. And then I think he's been spreading some of his knowledge and spreading the wealth of 3D printing to some of his classmates, because I hear him come home and say, oh, so-and-so bought a printer, and I like to think that we had a little bit of part in that. So it's awesome to hear that kids are interested in manufacturing, right? Being physical creators of stuff. So I see him as more like the engineer on stuff. Or my daughter, she likes to use 3D printing more for artwork. She loves to create earrings and, different like show and tell pieces. They might be pictures or light boxes or something like that. And as a dad, I like to, I certainly help them and engage them in it, but stand back and watch them a little bit too. And there's been some really incredible moments, for me in this. My daughter said that she wanted to print the Benchy earring. The Benchy is the little boat that's created like 10 years ago, is the benchmark for FDM printing. And I asked my daughter, well, why do you want to go create these earrings? And she's like, well, they represent 3D printing and they represent STEM, and that made my dad's heart just melt hearing that they're interested in, science, art, math. So that's really, really cool, right? So she's finding her interest in that. Where, my son, the more he engages in this, there's just some really neat questions that he's asking. And we're talking, about modeling and how do you take the models to the printer. And he was asking, well, he's like, why do some of the models that we have these little like facets in them? I think he called them steps or something. And I remember this was sort of late at night. We were up designing something. And the cool moment for me was we got to pull the book off the shelf that we wrote a couple of years ago. And I have an image in there that shows a resolution of STL files. And I got to show my son, this image of the different resolution, why you get some of that faceting in there. And for him, like, it clicked. And it was just this awesome full circle moment that he's learning about this. I was able to show him in the book that we wrote on metal 3D printing, so just spreading that knowledge and spreading that wealth. And I hope to continue to do that, and, not just for my kids, but for others, again, in work, outside of work. And, I'll fully provide an open disclosure on this. The book that we wrote, we don't make anything off that. I don't make anything off that. That was something that we did as part of our civil servant duties. But the class that we're talking about, the master class, all of our lessons learned in there. And I think, we said physically it took a couple of years to write the book, but really it was 25 years to write that, because we captured all these lessons learned. So you're probably getting millions of dollars in failed parts and challenges and issues that we had at that. So overall, I think education, mentorship is really important. I think you're never too old or never too young to be a mentor or be a mentee, right? Because I learn a lot from my kids as well. So there's times when they're mentoring me. So take that time, whether it be your colleagues or industry partners or your kids, because I think it will pay off dividends. Another saying that I've always had was, let's go build a better world layer by layer. And I think you can take that a lot of ways, whether it means additive or, building upon other people's knowledge on this and pay it forward.
Well, now we have to stop this episode, because there's no better ending than build a better world layer by layer. That's awesome. It's so beautiful to see how you and your kids have this fun experience that binds you together as a family, but also educates them and creates that creativity, ingenuity, tech insights. It's super cool to see. And I agree. You're never too old to be a mentor or a mentee. I think my son is teaching me he's too resilience right now and patience. But I'm really excited to take him down the additive journey as well. And I'm sure I'll come back to you for some advice here and there.
I can't wait to hear those stories, not just from you, but everybody. I love hearing those different aha moments with kids, right? And not just like 3D printing or technology, but the things that resonate. So, hopefully that's something that in this podcast that you can get comments on that. Tell us your aha kid moment with technology or 3D printing or whatever it might be.
Please do. Paul and I will keep an eye out, and we'll make sure to also answer every comment. Well, Paul, it was so awesome to have you back on the show. The journey continues. I'm really excited for this joint program, for this masterclass that I just mentioned. So if you're out there and you're wondering, man, I would love to meet Paul in person, get my book signed, and learn from him, from all these 25 years of experience that are packaged in the book and that we're also then packaging in this training. Sign up, and if you have any questions, please feel free to also shoot us an email. Paul, thanks for being on the show. It was awesome to have you again.
Thank you so much for having me. It's always a pleasure just to sit around and talk additive.
Exactly. And we're going to build a better world, therefore, layer by layer. Like we just discussed, comment, give us a review, and share this episode with your additive and non-additive friends. This was the Additive Snack Podcast, and I will see you next time.